Sorry, Mike, by the way, I also just sent an email to correct the name of the university you say. I at least write down the CU you say, it's not UC.
Right. Yeah. Whenever I see UC Boulder, it almost feels like people are making a joke that we're another branch of University of California.
Why I just sent a new email and also reminded for that. University of Colorado. Okay.
Yeah, it's very confusing because it's University of Colorado, but it's CU.
We'll probably wait for Nati Cyber. He will be here probably. I think likely. Usually he will be here. So
yeah, he told me he was coming actually.
Yeah. So when he is here, then we can. I think we can start. And people will still coming in, but we can just. The talk can be like 90 minutes, and you can feel free to expand or shorten your talk. It's not a really.
Okay. Sounds good. I probably.
So you take your time.
I saw that. Yeah, I probably prepared not 90 minutes of material, but maybe a little more than an hour. But that's good because then I can go. I don't have to rush, and there's plenty of time for people to ask questions. So that's good.
Okay.
Morning, everybody.
Oh, hey, Marcus.
Hi, Mike. So I thought I'm too late, but luckily I'm not.
No, we're just about to start, I think. Oh, Juven, I see Nadi is here now.
Yeah, so I think...
yeah, I'm here. I've been here for a while.
Ah, well, okay.
Are you waiting for me?
We don't see your name, though.
I do.
You don't see my name?
I see your name.
Earlier.
Do you see my face now?
Yes.
Okay, so maybe we can start. I think Okay. Welcome, everyone. Welcome to Harvard CMSA Quantum Matter in Math Physics seminar series. Today, we are very honored to have a Professor Michael Hermele from University of Colorado, Boulder. When people think about Colorado, I think we are going for the hiking mode. So, and also today is also a special day that the professor you just mentioned, Chinese New Year's Eve. So we have a very many events today. But even more happier, we are happy to have a Mike telling us a new story. His adventure on fractal and gap system, exotic quantum matter. His title will be Families of Gap Systems and Quantum Pumps. And let's just welcome Mike directly. Please take over.
Okay, thanks, Juven, and good morning, everybody. Thanks for being here. Actually, I think at least by his Zoom background, Juven looks like he's in Colorado, so in spirit anyway. Although if you actually go to that spot right now, it will be covered in snow and probably pretty cold. So I want to tell you about some kind of new work, and it's still work in progress. So let me start by acknowledging my collaborators. So it's actually quite a number of people are involved in this work. Some of them are here in the audience. And notably, this actually is part of a collaboration between physicists and mathematicians. The work that I will tell you about today is much more on the physics side of this collaboration. There are other threads of work that we're doing, which I won't have a chance to tell you about. And I particularly want to highlight the contributions of Shuida Wen, who's actually a joint postdoc between Harvard and Boulder, a part of the UQM Simons collaboration, and also student Marvin Chi, who's working with me at Boulder. Also contributions, so input from Ashwin Vishwanath and Agnes Beaudry, who's a colleague of mine in the math department at CU Boulder, are quite important for the story I'm going to tell you today. But I also want to mention by name my other collaborators in the math department at CU Boulder. So Marcus Flom, who I see here in the audience, and Juan Moreno and Daniel Spiegel, who may be here, but I'm not sure. Okay, so with that, let me just kind of introduce the problem. So what we want to do is think about a generalization of the usual notion of gap phases of matter. Okay, so let me just define the problem and then I'll give you some examples and motivation why this is interesting. So let's think about quantum many-body systems in d spatial dimensions with a local Hamiltonian and an energy gap. And there's some parameter space X. It could be any topological space. And some terminology is a gapped system over X. You can think of as just a continuous map from X to some space of gapped Hamiltonians. So we can say this is a family of systems parametrized by the space X, but we'll call that a system over X or a gapped system over X for short. Okay, and we're interested in not just in systems over X, but we're interested in phases over X, which more or less you can think of as deformation classes of gapped systems over X. So think about homotopies of this continuous map. So there's some parameter, you deform the whole continuous map all at once without closing the gap anywhere on X. And then that's a deformation of this system over X. The other thing that you can do to deform the system, of course, as usual, is you're allowed to stack with a trivial system. Okay, but I won't go into that in any detail. Now, how does this generalize ordinary gapped phases? Well, if you take X just to be a single point, then this just reduces to our ordinary notion of gapped phases. Okay, because a gapped system over a point is just a single gapped Hamiltonian. And then deformation classes of those, well, you consider paths in parameter space that don't close the gap. Okay, so so let me just mention that there's been some recent related prior work on this kind of problem. And some of this is going to figure in this talk. So I'm not going to go through these works now, but at least some fraction of these works are going to come up as we go here and there. Okay, so let me start with a really familiar example, which I think is probably familiar to everyone. And this is not many-body physics. This is just this is few-body quantum mechanics. So it's a zero-dimensional system. The parameter space is a two-sphere, and our Hilbert space is just a single qubit. Okay, and we have a map from S2 to Hamiltonians for the single qubit, which is just given by this dot product between the position vector on S2 and Pauli matrices. Okay, so this is actually the example to illustrate Berry phase that appeared in Berry's original paper. So it should be really familiar. And one thing that we can say about this example, which is interesting, is that if we imagine we start in the ground state of the system and we slowly change parameters going around the boundary of this disk on the sphere, then all the ground state wave function can do, if we really do this change slow enough, is pick up a phase. Now there's going to be some non-universal contribution to the phase that we're not really interested in. It just comes from the energy, really. But there's also a geometrical contribution, gamma, and that can be written as an integral of a one form called the Berry connection on parameter space around the boundary of this disk, or it can be written as an integral of a two form over the disk itself. That's the Berry curvature two form. In this case, the value of the integral is equal to the solid angle subtended by this disk divided by 2. Okay, and one thing we can do with this is we can integrate the Berry curvature over the whole two sphere and divide by 2 pi, and we get an integer, which in this particular system is 1, and that's the Chern number. Okay, so a little bit more mathematically, the ground states of this system form a line bundle, and the isomorphism classes of that line bundle are characterized by its first Chern class, and that's what this Chern number is measuring. Okay. But we should think of this Chern number as being an invariant of this family of quantum systems over S2. If we deform this system, keeping the gap open, there's no way to change the Chern number. All right, so that's a familiar example. Here's another familiar example, which gets more to many body physics because it's not a zero-dimensional system anymore. So this is what's called the Phalus charge pump. So now let's consider a one-dimensional system with parameter space of S1 and a U1 global symmetry. So I'm not going to write down a Hamiltonian for this system, but I'll just tell you about some of the phenomena. So imagine that we make the system semi-infinite. Okay, so it has an end, and this is the end. And then imagine we cycle the parameter around the S1. So what happens is that there's a charge flow from the bulk. And one way to see that there's charge flow from the bulk is to look at the energy spectrum of this semi-infinite system. And what we find as a function of the parameter theta is that there's a single crossing point. And on one side of the crossing point, the ground state has charge Q. On the other side, the ground state has charge Q plus 1. Okay, and the only way to interpret that really is to say that, well, there had to be charge flow kind of from infinity on the left to this end state. Okay, another thing that you can say about this is that if you just think about a zero-dimensional theory for the end, well, there's an anomaly here because it's not possible to consistently define the charge of the ground state as a function of theta. Right, the charge jumps by 1 at this gapless point, but there's no other corresponding gapless point where the charge jumps back. Okay, but the physics here is really charge flow from the bulk, and there are other ways to characterize it. Okay, so oh, I should say, you know, please do interrupt and ask questions. Okay. Okay, so what am I interested in this talk? So there are really a couple of questions. So the first question is just what kind of gap phases over X are possible? What kind of examples do we have? And what are their physical phenomena? Okay, so I think I'll hopefully convince you that there are lots of examples whose physics has not really been explored. And in some of these examples, there are some pretty interesting physical phenomena. And you know, we're still in the process of exploring many of those phenomena, and I don't think we've found all the interesting examples yet. Another question that I think is interesting to think about is how to realize these systems and how to probe these phenomena. I think that actually with some of these systems, because models for them are actually extremely simple, that may actually be pretty promising, but I'm not going to talk about that today. Okay, so this is a good place to mention some other prior work, maybe not as recent. Okay, and first I'll just make an observation. It's a kind of obvious observation that phases over an n-dimensional sphere are basically the same thing as defects of codimension n+1 in space-time. So imagine you have a defect core, and then you think about a map from space-time far away from the core to parameter space. And that space-time minus the core for a defect of codimension n+1 is going to have a homotopy type of the n-sphere. And so that map that you get when you have a defect really is the same as a system parametrized by Sn. Okay, so it's important to mention that connection. That connection's not going to come up so much today, but it's important to connect to some prior work. The first thing to mention is that both phases over n spheres and the corresponding defects were studied quite thoroughly 10 years ago by Teo and Kane in free fermion systems. Okay, but I'll be talking about interacting versions of the problem today. Although some of the things I'll say will also apply to free fermions. Another thing to mention is that actually there's been a lot of work on spatial point defects in two-dimensional topologically ordered phases, so phases with anyon excitations, non-invertible phases, sometimes under the name of twist defects or genons. And this has been studied by quite a number of authors, so I didn't want to try to list everybody here who's worked on that problem. I don't think the connection there to families of systems over S1 was made. Maybe it was made in some of that work. There's a lot of literature there, but it's not usually emphasized, but that is some important prior work. Another line of work that this is definitely connected to is flow K topological phases. So these are this is now in the realm of non-equilibrium physics, where you have a system with a periodic drive as a function of time. And in order for anything interesting to happen, we believe there needs to be many body localization, and there can be interesting topological phases, we think, in such systems. And those topological phases should be related somehow to phases over S1. And if you know something about classifications of these Floquet topological phases, that relationship is apparent. But the precise nature of the relationship might be subtle, okay, having to do with partly having to do with thorny issues that I don't think are fully sorted out in physics of many body localization. Okay, so that, I mean, what the relationship is in that last case is, it's not nearly as simple as this correspondence between, say, phases and defects. I think there are open questions there, but there is some connection to work that people have done in the Floquet literature. Okay, so here's an outline of the rest of my talk. So I'm going to start by talking about some generalities on families of invertible states over X. So I'll say what we expect about I'll tell you what we expect about how to classify such families. So a lot is known with kind of, I would say, minimal assumptions about how to classify such phases. And then I'll talk about the physics of these systems in terms of quantum pumping, and I'll tell you what I mean by that. Then I'll give you an example, which was promised in the abstract, this Chern number pump. It's a one-dimensional system. And then I'll talk about ways to get to other kinds of families of systems starting from an invertible family. So at least in some cases, if you start with an invertible family with symmetry and you apply a duality transformation, you can get a family with broken symmetry, okay? Or in other cases, if you start with a family, again, with some symmetry or fermion parity maybe, and you gauge the symmetry or the fermion parity, then you can get a family of non-invertible topological phases, okay? So there will be a bunch of examples and I'll try to highlight various phenomena in those examples. Okay, so first of all, let's remember what an invertible phase is, just briefly, okay? So it's a gap phase. It has no fractional excitations in the bulk. If you put it on a closed manifold of non-trivial topology like a torus, the ground state is unique, and these phases form a group under stacking, if you just put two of them together in the same space, okay? So there's an expectation that will be important here that we'll use, which is that invertible phases over X should be classified by a generalized cohomology theory. Okay, so I'll explain that a little bit. This really comes from ideas of Kitaev, which are also explained in a very nice paper by Gaiotto and Johnson-Freyd, which I encourage you to read. And I'll say a little bit about this because the point of view that I'll use is slightly different from the point of view that's taken in those works, but it's really, you know, I don't think I'm really saying anything new in this part of the talk. Okay, so okay, so one way to think about where this expectation is coming from, it follows from the assumption that gap phases form something called a loop spectrum, okay? Which appears prominently in those works. So what I want to do is I want to fix certain attributes of my system. So I want to decide at the beginning if I'm dealing with fermionic or bosonic systems, and there may be some symmetry involved. So I want to decide on the symmetry. Okay, and so now that's done. And we imagine that we can define a space, a topological space called ED, which will be the space of d-dimensional gapped invertible phases with those desired fixed characteristics. Okay, that part is a little different from in those works. Usually they're interested in starting with phases without any symmetry and then trying to use that to understand the classification of phases with symmetry, but that's actually more than what I will need for my purposes today. Okay, and it's possible to argue that there are homotopy equivalences between the space of d-dimensional phases and the loop space of d plus one-dimensional phases. So this is the space of loops in the space of d plus one-dimensional phases. And I'm not going to go through the argument for why there should be homotopy equivalences. It's a pretty physical argument just in terms of drawing pictures. Actually, one of the pictures will come up in this talk a little bit later, but I'll use it. The point of view will be slightly different. Okay, but if you want to know why this should be true, you can look at Gaiotto, Johnson-Freyd's papers, and they draw all the pictures, and you can get a feeling for why this should be true. Okay, so from these assumptions, just mathematically, so this is really the statement that these spaces form a loop spectrum. So then what you can do is you can say, well, let's think about, now we introduce a parameter space X, and we think about homotopy classes of maps from X to the space ED. And essentially, I'm glossing over a little bit here, but essentially, that will give us a generalized cohomology theory, which depends on X. So I'll write that as E upper D of X, and that's an abelian group of, that's the abelian group of phases over X. Okay. All right, so that's kind of where this expectation comes from.
Question.
Yes, Nadi, go ahead.
Do you exclude points with gapless points from X or not?
Yes. So X, so the maps from X to ED that appear here, so ED, they're excluded. One way to think about that is that ED is a space of gapped Hamiltonians or gapped systems. And so we only, every point in X has to map to a gapped Hamiltonian. So we insist that the gap is always open for every point of X. And that's important because if you allow the gap to close at some points of X, you might be able to, well, that's going to result in, at best, a coarser notion of phases. There, it'll allow you to make more deformations than you would otherwise be able to make.
I understand this point. What I find baffling here is that in order to know whether the system is gapped or not, you need to solve the system. And the parameter space X is defined at short distances. You don't care what the system will eventually do with long distances. So you kind of use more advanced information in order to define X, which is okay. But the broader point of view would be that you study the whole space, and then by following analysis similar to yours, you might reach the conclusion that there must be a gapless point in between.
Yeah, that's right. I see what you're saying. Yeah, I mean, it's certainly true. Right. Well, let me make a distinction though. Okay, so X is not, you don't want to think of it as the parameter space of all d-dimensional systems. That's actually this space ED. And understanding the space ED really in any detail could be extremely difficult, precisely because it's hard to tell whether any given system is gapped or not. But X is usually going to be some small familiar space, like an n-dimensional sphere. Think about this example that I started with for Berry phase, right? So there's some map from, some explicit map from that space to Hamiltonians, which in that case are manifestly gapped. The examples that I construct today, the Hamiltonians will be easy to solve, and so we'll know that they're all gapped. Of course, you can deform, those families can be deformed such that they involve Hamiltonians for which deciding whether or not there's a gap is a very difficult dynamical problem, right? But that, I mean, we're used to having that issue arise all the time, even for ordinary phases. I hope that helps.
Thank you.
Okay, so so we can say some things just from this expectation that there's a generalized cohomology theory. That's kind of why it's going to be useful. So the first thing is, let's pick a base point in our space, just arbitrarily pick some base point. And if we pick a base point, then the group of phases over X can be written as a direct sum of two pieces. One thing that comes in is just the generalized cohomology theory over the base point, okay? And then there's whatever is left over, okay? And physically, the way to interpret this part, this is just ordinary d-dimensional phases. So it's phases over a point, and we should think of this from, this comes from families of systems that are constant over X, where there's no dependence on X at all. So this summand is kind of boring. Although it can actually still lead to interesting phenomena sometimes, but certainly from the point of view of classification, it's a little bit boring. The stuff that's left over is more interesting. So these are phases over X that don't come from constant families. So for example, if you have a non-trivial element of this E tilde of X, it must not be possible to deform that family to a family where the Hamiltonian has no dependence on X. Okay, Juven, I see you have a question, but let me say one thing first. So, and mathematically, the tilde here actually means something. This is actually the reduced version of the generalized cohomology theory. But if you don't know what that means, just think of this as phases over X that don't come from constant families. Yeah, Juven, do you want to go ahead?
Just make sure.
Oh,
So,
sorry. There are two of you, I see, and one of you is raising your hand. Okay, I got a little confused there.
I think the host cannot raise hands, so I use another one.
I see.
So you're classifying family of gap phases given by certain space manifold X or space-time space.
So X is parameter space.
Space.
So it's not space or space-time. The space dimension of space shows up in the D here. Sometimes people would use space-time, but for me, little d always means spatial dimension. Yeah, but I haven't said anything about the space-time manifold.
So how is the X given then? Just make sure, maybe I missed.
Well, it's just given from the beginning, right? Like, think about it maybe helps. Oops. Now, what did I do? Go back to our first example, right? We just declared that I want to consider a family of Hamiltonians parametrized by S2. And I defined some map from S2 to Hamiltonians, right? In this case, to few body Hamiltonians, but you could do that for many body Hamiltonians as well. So okay. It's just a piece of data that you have to specify at the beginning to talk about the system.
And just make sure, because you have a spatial best point X, would you call this X space as a pointed topological space or something like that?
I mean, it depends. It depends. Like sometimes you want to consider it to be pointed, sometimes you don't want to consider it to be pointed. I mean, here this is the usual isomorphism between unreduced and reduced cohomology theories that you get when you pick a base point. And so, really the X on the right hand side of this isomorphism you should think of as a pointed space, and that means something physically. To say that the space is pointed, what you really should be saying is that the Hamiltonian for the base point is in the trivial ordinary phase. It's in the trivial ordinary phase over a point. So if you pick a base point for which that's always true, then you should think of as you're working with pointed spaces. So there is a physical meaning to working with pointed spaces or not working with pointed spaces in this setting.
But if there's a spatial base point, let's say, what would be the meaning for that in the parameter space? Is that the
no, not a spatial. It's a base point is in parameter space.
Yes, I mean
yeah. So right. Let me say that again. So if you pick, maybe I should write something.
I mean, sorry, my pronunciation problem. Just special.
Right.
Unique.
Yeah. So if X naught is a base point, then this will map to some Hamiltonian, which is just a function only of the base point. And if we're working with pointed spaces, we would assume that H of X naught is in the trivial phase. And here I have to say, it's confusing. It's trivial phase over a point. It's the trivial ordinary phase. Okay. You don't have to make that assumption. If you make that assumption, then it's sort of more natural mathematically to work with pointed spaces. So you can choose to do that or not do that. Okay, I see there's a bunch more questions.
Just make sure one more time. Will this pointed, suppose it's pointed, will this is a unique point, the unique one, would that be identity Hamiltonian or something like that?
No, the Hamiltonian doesn't have to be, it just has to, the Hamiltonian over that point just has to be in the trivial phase. It doesn't have to be like, the ground state doesn't have to be like a product state or something really trivial like that.
Okay. No, thank you.
Yeah, okay, so Andre, I think, had a question, and then Fiona.
My question, you may have answered it partially by answering Juven's last question. So you define the left-hand side, this E superscript dx, as a homotopy class, right, from X to this ED space.
Yeah.
And so usually the way homotopy is defined, you need to specify So unless X is simply connected, you have to say with respect to which point you're defining the homotopy. So is the assumption here that X is always simply connected, the parameter space of your Hamiltonian?
No, let's see, I think, well, you can consider, yeah, I mean, now this is, I may say something wrong here because I'm not really going to use this at that level of detail. But you know, you can consider homotopies that are based or not based, right? Where
Exactly.
and it's a choice, and I think that really corresponds to whether you're doing unreduced or reduced cohomology.
Right.
But let's not worry about that too much, because it's not really going to matter for what I want to focus on in this talk.
Gotcha. But this discussion is separate from the question of pointed spaces that Juven just asked?
No, it's related to that question. Yeah.
Okay, very good, thanks.
Yeah, Fiona?
So I just wanted to double check. So this EDX naught, I should think of this as being, you know, whatever gapped Hamiltonians I can write down that like don't care whether they're, you know, I somehow send the system through a non-contractible loop-in parameter space. So these are, you know, somehow like, well, I guess, so necessarily that is the trivial phase, or is there some, am I missing something?
No, okay. So I mean, so here's a really there's a really trivial way to get a system over X naught, which is you just take the Hamiltonian to be independent. Sorry, there's a really trivial way to get a system over X for any X, which is you just say, take my Hamiltonian to be completely independent of X. It's kind of boring, but you can do that. And if you do that, then you're really just looking at ordinary phases, just phases, you know, that are not parametrized by anything. Okay.
But like,
you know, you can take this family like, yeah, go ahead.
Yeah. I mean, so yeah, I'm a little confused about when you say ordinary phases, like that would also include like a topological insulator and stuff like that, or?
Yeah, that's right. So ordinary invertible phases, right? So for, I think maybe this will be clear. I'll show some examples in a minute, and I think maybe
yeah. So sounds good.
Bother me again in a couple slides if I haven't clarified this, because I think I
sounds
will.
good.
Yeah.
Thanks.
Okay. All right. Good. All right. So there's another thing I want to mention, which actually is this sort of is what is doing all the work to generate interesting examples. So there's an isomorphism in any generalized cohomology theory called the suspension isomorphism. So I need to explain this because it's going to play an important role. So take a space X and cross it with an interval. Oops, that's not what I wanted to do. I want the pointer. Okay, and from this you can form an identification space where you collapse the top. So this is a cylinder. You can collapse the top X to a point. You can collapse the bottom X to a different point. And so that's, you know, you have a map that makes that identification, and the resulting identification space is SX. Now, if you look at this picture, X here really is S1, and it's pretty easy to see that the space SX is homeomorphic to a two-sphere. Okay, and in general, this acts nicely on spheres. So the space on the right is called the suspension, more precisely the unreduced suspension, and S of Sn is always homeomorphic to Sn plus 1. Okay, so it turns out that for sufficiently nice spaces like we'll always work with, think like closed manifolds or something, the reduced cohomology in D dimensions for X is isomorphic to the same thing in dimension D plus 1 for the suspension of X. So that's the suspension isomorphism. Okay, and this has an important consequence if we want to think about phases over Sn. Okay, so here's the group of phases over Sn. All right, so first of all, there are some constant families that are boring. And then if we use the suspension isomorphism, let me not explain maybe every step here. What we see is that D-dimensional phases over Sn, the classification of them is the same as D-dimensional phases over a point and D minus N-dimensional phases over a point. Okay, and it's really this summand which is interesting. Okay, this is where the interesting examples come from. But the point is that just this assumption of a generalized cohomology theory, it tells us the classification of phases over Sn in terms of phases over a point, which generally we already know about that, at least in low dimensions. So we don't have to sort of redo the whole classification story here. Okay, so let me now kind of use this, give some examples, and I hope this will clarify Fiona's question. Okay, so let's think about bosonic systems with U1 symmetry, right? So this includes the Phalus charge pump that I talked about. So this is the group of all these phases. This is the space. PT is a point, and here's S1. And then we'll look at spatial dimensions 0 and 1. So in dimension 0, phases over a point, these are ordinary phases. Well, there is something because there's just the U1 charge of the ground state, and that's an integer. Okay. So there's a Z classification in 0 dimensions. Okay. Now, suppose we go up to S1, still in 0 dimensions. Well, this Z still gets copied to the right. Why is that? Well, if you have a ground state, which if you have a system, 0-dimensional system, which depends on a parameter in S1, the system is always gapped, you can still ask what's the U1 charge of the ground state. It'll be the same everywhere on the S1. It can't change. Okay, so that's true. And so there's still a Z classification over S1. But that Z over S1 is not that interesting because any family like that can be deformed to a family where the Hamiltonian doesn't depend on the parameter of the S1 at all. Okay, so these are kind of not that interesting. Okay, and that corresponds to this summand ED of X naught. All right. Now, if we go up to 1 dimension, it's more interesting. Over a point, there's nothing. There's a trivial classification. But over S1, there's again a Z classification. And you can obtain, even if you didn't know about the Phalus charge pump, you can get that Z from this assumption of a generalized cohomology theory. It really just comes from applying this formula. Okay. All right, and there's just a diagonal structure here. So this Z just gets copied again here. And in this case, we know that example, we know how to write down Hamiltonians for it. It's the Phalus charge pump. Okay, so it's familiar. Now, it's sort of annoying to draw these examples that just get copied from 0 dimensions that correspond to Hamiltonians that don't depend on parameters. So a way to do that is to plot the reduced cohomology instead, a way to ignore them. And so then we don't have anything over S1 in 0 dimensions. So this is not really the group of phases, but now what we're doing is we're showing invertible phases that if they're non-trivial, they can't be deformed to constant families. And for some technical reasons, I'm using S naught here instead of a point, which is S naught is 2 points. That has to do with base points, but let's not worry about that. It's kind of too much getting into the details maybe. Okay. Let me do another example, which is what we're going to focus on in a minute. So how about bosonic systems with no symmetry? Well, in 0 dimensions over S2, we have the Chern number. This is the example that we started with. There's a Z classification, and that should get copied on this diagonal. So there should be another Z in 1 dimension over S3 and another Z in 2 dimensions over S4. And here's the E8 state in 2 dimensions over a point. So what are these Z's? Well, they're not as familiar. So this one I'm actually going to talk about quite a bit in just a second. So this I'll call it, this is a Chern number pump. There's also a pump of a Chern number pump, which we know some things about, but I'm not going to have time to talk about it today. Okay. All right, so none of this is that helpful if you don't if you don't know how to construct examples. Knowing that the classification should be Z here and Z here, it's maybe not that useful. But there's actually a machine that can construct all these examples for you. Really, just a straightforward procedure. It's just it's routine. So if you know a model for this example, I can produce for you a model for this example, and in turn, we can write down models for that case, and so on. Okay, so that's what I want to explain next. So that's what this construction is. So it comes from ideas of Kitaev, also explained in this paper by Gaiotto and Johnson-Fried that I mentioned. It actually, this construction comes from the same pictures that are used to construct homotopy equivalences between these different spaces, but it's being used from a slightly, the perspective here is slightly different, but I think it's essentially the same idea. So how does the construction work? So suppose that we have some d-dimensional gapped invertible system over X. Okay, X could be a point, but it doesn't have to be. And let's denote this system just schematically by S sub D. And suppose we have its inverse. So some system where if it's invertible, so if you stack it with its inverse, you should get a trivial phase. And what we want to do is construct a D plus one dimensional system over the suspension Sx, and we'll call that system the suspension of SD. Okay, so what we do is we start by constructing a system over X cross an interval. Okay, so and it's a D plus one dimensional system. So this axis is the D plus first spatial coordinate. T is the coordinate in this interval. And first look at T equals 0. What we do is we just simply make an array. We make a lattice of d-dimensional layers, and therefore we get a D plus one dimensional system. And we just make an alternating stack of the system SD and its inverse. Okay, so that's something we can definitely do. And then we observe that, well, let's look at this pair of a system and its inverse. So that system, that because it's a system SD stacked with its inverse, it's in the trivial phase over X, and so it can be deformed to a trivial system, to a trivial state. Trivial state means just a product ground state where there's no longer any dependence on X at all, right? So this is in the trivial phase over X, this bilayer. This oval means actually a trivial state. So it's really a product state, and there's no dependence on parameters in X anymore. Okay, so there has to be some path that takes this bilayer to a trivial state. Okay, so we can, that's what we use between T equals 0 and 1, okay, to construct a family over that part of the interval. And then we have a different path. We compare systems in the other way, right? This is one dimerization. This is a different dimerization. We pair the other way. We also have a similar path. Doesn't have to be the same path that goes from 0 to -1. Okay, so this gives us a family over X cross an interval. But what we observe is that at the endpoints of the interval at T equals plus or minus 1, the Hamiltonian actually doesn't depend on the parameters in X by assumption. And so that means that we actually get a system over the suspension, right? The map from X cross the interval to gapped Hamiltonians factors through the quotient map that takes you to the suspension over X.
Mike, sorry, could you clarify the notation? Yeah. The sort of the red. Okay, so the red oval over the two dots, right? Each of which is a SD Hamiltonian. Yeah. What does that mean? So how do you?
Yeah. So each dot here is a d-dimensional layer. Okay, and these red ovals are a trivial system over X on a bilayer. Okay.
On a bilayer.
Not just in the trivial phase, but actually a trivial state. So it's a product state, and the Hamiltonian's independent of X on these two d-dimensional layers.
I see, but the bilayer means what? Formally, it's a map from X to SD cross SD. What is the target?
Well, bilayer is just it's just two d-dimensional systems. It's really a bilayer. Yeah, the horizontal axis here is physical space. It's one direction in physical space. So if little d is 0, then we're just making a chain, yes. And then the chain, and we're really just showing pictures of this spin chain as a function of t, basically pictures of its ground state.
Gotcha. So, and the idea of the oval is that you create a trivial system out of the two layers, correct?
Yeah, that's right.
Thanks.
Mm-hmm. Okay, so this. Let's see. Yeah. So now I could try to say some things about the formal properties of this construction, but I don't want to dwell on that, partly because we're still sorting out some of them. But let me just say that we expect that this construction should realize the suspension isomorphism on phases. Okay, that's the belief. And we have arguments at least for some parts of that. But maybe not arguments for all of it, but that's okay. So we believe that this should realize the suspension isomorphism on a group of phases. So let me also just tell you about a slightly modified version of this construction, which gives a D plus one dimensional system over a different space, which is X cross S1. And this is kind of important when we think about the physics of pumping, because now what we're doing is we're adding a periodic parameter. So I'll call this system PSD, where the P stands for pump. And how do we construct this family? Well, we start with the same idea. And in fact, so now theta is the coordinate of the S1. From 0 to pi, we construct exactly the same family that we already started with. But now we realize that at theta equals 0 and theta equals pi, we have two states in the trivial phase over X. Actually, there's no dependence on X. So really, these are states in the trivial phase over a point, and there has to be a path between them. So you have to be able to deform them into one another actually without any dependence on X. So the Hamiltonian does not depend on X in this interval at all. It only depends on theta. And you can deform through a system which is actually trivial on each layer individually. And there may be some modest assumptions that you need in order to make this actually work, but I don't really want to get into that. I think they're very mild technical assumptions. Okay, so so we can construct families over the suspension, one higher dimension, or over X cross one in one higher dimension. Okay, so now I want to tell you, even before I talk about specific examples, I'm going to need to talk about spatial boundaries. So I want to make some general remarks about spatial boundaries that are important to understand. So suppose we have a d-dimensional system over X, any d-dimensional system over X. So now what I want to do is consider a system with a spatial boundary. So in general, the parameter space can be bigger than actually X. So we'll call it X boundary, and there has to be a surjective map from X boundary to X. So why is this? Well, this is just reflecting the fact that the Hamiltonian near the boundary could depend on some extra parameters that the Hamiltonian near the bulk doesn't depend on. Okay, so this is just the most general situation. The simplest case, of course, is just that X boundary and X are the same. So the Hamiltonian only depends on the parameters in X, that's it. And if that's true, we expect there to be, although this is the sort of thing that we don't really know how to prove for invertible phases at all, even ordinary invertible phases, but it's a usual expectation. If X boundary is the same as X, there's a kind of bulk boundary correspondence. And that would take the form that we would say that the phase of SD is trivial if and only if the boundary can be trivially gapped over all points in X. What does trivially gapped mean? It means that there's no symmetry breaking on the boundary and there's no boundary topological order. Okay. Now, if X boundary is larger than X, okay, then actually it may be possible to trivially gap the boundary even if the bulk phase is non-trivial. And I'll show some examples of that. So that's why I want to make this remark, because it's sort of when you can and cannot gap the boundary depends on what the boundary parameter space is. So that's an important thing to understand. All right, so let's think about this example over X cross S1, sort of general example. And now let's give the system a spatial boundary. So we just truncate it here in space. And okay, and what we want to look at is what happens at X equals pi. So if you just take the naive boundary truncation, the system is obviously gapless, and it's actually highly degenerate at theta equals pi, because this d-dimensional layer is just not paired with anything. So the Hamiltonian for this whole layer is 0. Now that's obviously very fine-tuned, but that's what happens in this naive boundary truncation. So on one side here, here we have SD. Okay, so the boundary, the phase of the boundary over X you can think of as being SD, and here on the other side you have the trivial phase, and there's a gapless point between them. Okay, now because we can argue that if SD is non-trivial, then PSD also has to be non-trivial. What that means is that this gapless point, even though this is very fine-tuned, you can't completely get rid of it. You could definitely change what happens at this gapless point by adding various perturbations on the boundary, but you should not be able to gap it out, at least not trivially so. Okay. All right, but you can think of this as now Okay, but you can think of this in another way. You can think of this as a pumping of a d-dimensional phase SD to the spatial boundary. Andre, just a sec, I see you're raising your hand. So imagine you start just above this gapless point. The boundary is quote unquote in the trivial phase over X, and then you increase the parameter theta to here, and now the boundary is quote unquote in this phase SD. So it's like you've kind of pulled out an SD from the bulk and you've stuck it to the boundary. Okay, so that's why we say that, you know, the physics here is kind of, it's pumping of this lower dimensional invariant to the boundary. Okay, yeah, Andre, question.
Yes, Mike, I may have missed something fundamental about the Phalus charge pump. So maybe this misunderstanding on my part. I thought that in a Phalus example, the system always remains gapped, right? And hence the paradox, because you're not supposed to be able to move the charge through a system which is fully gapped, but because of this
in the bulk, yeah, I think what you're remembering is that in the bulk, the system is always gapped. But as I showed you at the beginning, yeah, if you take your favorite Hamiltonian for a Phalus charge pump and you put it on a semi-infinite system, then you'll find that there actually is a gapless point, one gapless point as a function of the parameter. And the gap closes, the gap closing is associated with some gapless mode that's localized at the boundary. And what happens is it's just a level crossing, so the ground state just changes its charge by 1 unit.
Right, but that's boundary is a physical boundary of the system, not a boundary in X space. I think here it would appear.
Oh, no. When I say boundary, I always mean boundary and boundary in physical space. Yeah, not boundary in, I don't know. I mean, yeah, the parameter space could be a manifold with boundary or something, but that's a totally different thing.
Oh,
yeah,
I see.
Here, boundary is boundary in space.
Oh,
yeah.
So when on the previous slide you define X boundary, what did you mean? Because X is this abstract space that doesn't. I thought you meant the abstract.
Yeah, it will be more clear in the next example what X boundary is. But the point is that there's nobody told you that you can't. Right? Whenever you truncate a system at a boundary, you can sort of always do whatever you want at the boundary, right? You introduce other terms in the Hamiltonian that have nothing to do with the Hamiltonian in the bulk. And when you have a parameter space, the boundary Hamiltonian could even depend on extra parameters that the bulk doesn't care about. So X boundary is the parameter space that you need to describe both the boundary and the bulk Hamiltonian.
Gotcha. Okay, now it's clear. This was my misunderstanding what you meant by boundary. Perfect.
Yeah, it's confusing because there are a lot of different spaces involved here. Xiaogang, it looks like you have a question.
Yes. When you say boundary is gapless, do you really mean the boundary is non-trivial? They could have a symmetry breaking or topological order, things like that.
Yeah, that's right. When I say, so here, in this particular example, in this particular boundary truncation, the boundary is gapless. Yeah, so whatever you do near that point, right, you may be able to gap out the boundary, but it would be at the price of symmetry breaking or topological order or something like that. Okay. Yeah, that's right. Yeah, there's no way to there should be no way to trivially gap the boundary.
Okay, yeah, that's
it. Okay, good.
So now, can I add a comment to that? It's a little more complicated, I think, because if you have something like a symmetry breaking boundary, you should expect that to happen in a whole region, and so it wouldn't really. Yeah, I'm not sure. You'd still probably have a gapless point as you entered the symmetry breaking region. So it's not clear to me that you can always gap the boundaries of these families.
If symmetry exists only at that point. So imagine a symmetry that exists only at that point in the parameter space, and then it is spontaneously broken, and then at other points it's not.
Yeah, of course.
Symmetry is not there.
But I think what Ryan is saying is there would be a phase transition. There would be a phase transition if you spontaneously break the symmetry. I think, Ryan, what you're saying is that if you spontaneously break the symmetry just near theta equals pi, then there will be some boundary phase transitions associated with that as you get near that point. But you could definitely spontaneously break the symmetry on the whole boundary. You need a finite, you can't do that with a small perturbation, but you can do it with a finite strength perturbation. And then you can fully gap the boundary for sure.
But there's sort of always a larger family where the gapless point is still there. You can never get rid of it.
I think Mike is saying that you take the whole X space, and then for every x you spontaneously break the symmetry, right? Then it will change the
Yeah.
the
Yeah, you can definitely choose boundary truncations where the boundary is fully gapped over all x. And you can do that keeping the boundary parameter space to be, in this case, x cross S1. It's not something bigger.
That's true.
Yeah, you can definitely.
I just think
do
it's that there's something
Yeah.
stronger than in the normal SPT bulk boundary correspondence where we just can't rule out a gapped boundary. Here, there will be, when we have this non-trivial family, somewhere in the boundary phase diagram, there are definitely gapless points. It can't all be gapped in the entire phase diagram. Maybe because you're looking at a specific parameter, circle in parameter space or whatever, some subset, that you only see these gapped points. That makes sense. But globally, there has to be some gapless points.
So why can't you have just topological order everywhere?
Yeah, I don't.
I feel like is make like an island, right? You can make like an island. It's like these diabolical points, right? Like you can have a gapless point.
This doesn't feel different to ordinary boundaries, though.
Huh?
I mean, I don't. But I feel like, unless I'm misunderstanding what you're saying, it doesn't feel very different to me than ordinary phases over a point and their boundaries. There's always some boundary phase diagram, right? Here, the boundary phase diagram, would be a phase diagram of phases over x cross S1. Let's say we don't ever enlarge the parameter space. And that phase diagram, everywhere in the phase diagram, you have to reflect the fact that there's a boundary anomaly. And there can be different ways to, that anomaly can be manifest in different ways, depending on what phase you're in, or at some boundary phase transitions.
Well, I think it's more like, well, anyway, let's talk about it another time.
We should maybe talk about it later, but yeah. Okay, so just a couple quick comments on this. So, basically this physics of pumping a lower dimensional invariant to the boundary. So, we're definitely not the first people to observe that. And so you can see on the slide some places where that was observed before. So, one question is, it sort of looks like that notion is very specific to this particular construction. So how can you make it precise? So one way to make it precise, which is maybe not my favorite way, but it's a reasonable way, is to invoke the notion of a d-dimensional boundary theory, which in this case over an interval x cross, so it's a subset of the S1, x cross theta 1, theta 2, should really just be an ordinary d-dimensional system. Okay, you should lose the non-trivialness when you just look over part of the S1, that we should lose the anomaly. And once you do that, then the difference in boundary phases on either side of the gapless point will be well defined in that boundary theory. The absolute notion of which gap phase you're in on the boundary is not well defined, and that has to do with the boundary, the fact that there is an anomaly on the boundary. Okay, but there's another way to make this well defined, which is also a different kind of phenomenon associated with the boundary, which is interesting as a physical phenomenon, but not just a way to make this notion of quantum pumping well defined. So I'll call this gapped quantum pumping. So here, let's take the parameter space of the boundary to be bigger. Okay, so I'll unwind this S1 into an interval 0 to 2 pi. And then, of course, there's a map from that space to x cross S1 where you just glue the two endpoints of the interval together. So here, the boundary is not periodic in theta, even though the bulk is periodic in theta. Okay, and then what you can do is you can say, all right, let's start at theta equals 0 with a boundary in the trivial phase over x at theta equals 0. Okay. In the bulk, nothing much changes. So here, what's happening? Well, so the boundary is not doing anything between 0 and pi over 2. Between pi over 2 and pi, we just swap this phase, which is one layer down, with this phase. So these just trade places. So we can do that. So the phase SD kind of crosses over into what we're calling the boundary. And to the left of this line that I'm drawing here, everything just proceeds normally in the bulk. Okay, so at theta equals pi, we have this. Then as we go up the next level, we just trivialize everything in the bulk. And then in the bulk, we go back to the original dimerization. Okay, but the Hamiltonian of this boundary system at theta equals 2 pi is different from the Hamiltonian at theta equals 0, because at theta equals 2 pi, now it's in this non-trivial phase SD. Okay, and this is all done while keeping the gap open. So the gap stays open here. Okay, and you can argue that it's not possible to do this if the bulk phase over X cross S1 is trivial. Okay, but anyway, this is some kind of quantum pumping. It's gapped quantum pumping. And the thing to notice here is that at theta equals 0 and theta equals 2 pi, this boundary system is actually totally disconnected from the bulk. So it's meaningful to just ask what d-dimensional phase it's in. Okay, there's no coupling between the bulk and the boundary at theta equals 0 and theta equals 2 pi. But because there was coupling at intermediate thetas, it's possible to change that d-dimensional invariant without ever closing a gap. And you can do basically the same construction for the suspension, this other family over the suspension. Okay, but it's kind of nice to think about S1 because that's more obviously pumping, because here the bulk is really coming back exactly to itself while the boundary is not. Okay, so now let me tell you a more specific example of a system. Rudro, you have a question. This is a good time to ask it.
Hi, Mike. This is a great talk. Could you please clarify if translational symmetry plays any role, or is it an important thing in these sets of arguments that you've made?
I think the answer is no. I'm not assuming any translational symmetry. You could assume translation symmetry or other spatial symmetries for these d-dimensional layers if you want. Some of the statements I'm making, you have to be a little careful about them once you bring spatial symmetries into the picture. Like, for example, what I said about bulk boundary correspondence would not be true in general for spatial symmetry. So you have to be a little careful. But yeah, so the symmetry, which is definitely, I don't think plays an important role, is translation symmetry in this direction. You may have it in the bulk, but you don't, at least translation symmetry by two layers, but you don't need it. You could break it at least weakly. And of course, that symmetry won't play a role once you look at the boundary physics and you truncate the system.
So the reason I'm getting a little bit confused is because you could think of a boundary of a system as where translation symmetry cannot work anymore. It's like you can't translate the system through the boundary. So if we think of translational symmetry breaking in the bulk as some kind of a how should I say, a much more benign version of having boundaries. Can we think of it that way, and what does it do to the kinds of arguments you are presenting? It could be simply no, that's fine. But
I think maybe I guess I think the best answer is I don't know. Like if you actually, so I'm not trying to rely on any translation symmetry in the bulk in the direction normal to this surface. If you assume it, it may change something, but let's just say I'm not imagining that symmetry is present necessarily.
I see. I mean, thank you.
So obvious families can be enriched by symmetry, right? You have symmetry protected families.
Of course,
which have new classification, and translation symmetry will be one possible symmetry that enriches the family, right?
Yeah, that's right. Yeah. In terms of the examples that I've thought about specifically, I've not thought about examples with spatial symmetry, but you can do a lot of this. Well, you can certainly consider families with spatial symmetry, and a lot of the things that I've said so far in the talk, although maybe not all of them, can be done with certain spatial symmetries. Okay, so now let me tell you about a specific example. Okay, so we actually, so this is I won't remind you of how the construction works, but I'm just going to write down the Hamiltonian because it's a really simple Hamiltonian. But where does this come from? So we start with our very first zero-dimensional example over S2, the Berry phase example. Okay, and then we construct a one-dimensional system over the suspension of S2, which is just the 3-sphere. Okay, so let's just write down the Hamiltonian as a function of coordinates on the 3-sphere. So, you know, coordinate, it would just parameterize the points on the 3-sphere by a unit 4 vector, okay, with entries Wi. So the Hamiltonian is a sum of 3 terms. The first term is just a sum of on-site fields with alternating overall sign. And so if you just look at one site, this is just the Hamiltonian for our 0-dimensional Berry phase example. Okay, right. So that's what W dot sigma means. What are the 2 other terms? Well, these are just sums. So the first one it's really just an antiferromagnetic dimerization between even pairs of sites. The other term is an antiferromagnetic dimerization between odd pairs of sites. Okay, and there are these functions G plus and G minus that go in front of those dimerizations. So G plus, basically you want it to be non-zero only in the northern hemisphere of the S3, and G minus, you want it to be non-zero only in the southern hemisphere. And this is a particular choice. They're both 0 on the equator and they're non-zero away from the equator. The particular choice is not so important. Okay, and notice that this Hamiltonian is trivial to solve because at any point on the 3-sphere, at most 2 spins are coupled at any one time. So it's just a bunch of decoupled clusters. But the clusters are different. You know, the organization of the spins into clusters is different depending on whether you're in the northern hemisphere or the southern hemisphere. Okay, and I won't write down the Hamiltonian for it, but you can construct a essential, quote unquote, the same system over S2 cross S1. It's the same idea. All right, so this is an example. So what's the boundary physics? Okay, so take the boundary parameter space just to be S3 and truncate the boundary in the kind of most naive way where you just throw out terms that would go to the other side of the boundary. So what happens here is that you just get a single gapless point at the quote unquote north pole of S3. Okay, because this spin doesn't get paired with anything at this point, and the single site Zeeman field terms are turned off at the north pole. They go to 0, right? Because these terms, when W4 is plus or minus 1, these terms are 0 because the other components of W have to turn off. And it turns out if you look at the Hamiltonian near this point a little bit more carefully, this is actually a Weil point. It's a diabolical point. And the interesting thing about the boundary from this point of view is that there's a single Weil point over the whole S3. And that's clearly anomalous because if you had an ordinary 0-dimensional system, the Weil points would have to come in pairs with opposite chirality. Okay, so that's that already tells us that this example is non-trivial, which we expect. What else can we say about it? So now we can also talk about how to characterize this this example in the bulk, and so we can take advantage of some recent results of Spodeneka and Kapustin. And actually that work was an important inspiration for a lot of what I'm saying. So what did they do? So they constructed, I'm not going to tell you the details because there's not going to be time, but I'll just give you a flavor. So they constructed a closed 3 form on parameter space. It's a form with quantized periods for gapped 1-dimensional systems. And they also generalized it to higher dimensions, but I won't use that. And you should think of this 3 form as generalizing the Berry curvature 2 form for 0-dimensional systems. And it's important to say that this 3 form, omega-3, it depends on a whole bunch of choices. And one of the things it depends on is picking a point in 1-dimensional space. And it actually has, in a certain sense, a local expression around that point. Okay, it involves correlation functions that decay exponentially away from that point. So even though this form depends on a bunch of choices, its cohomology class does not depend on the choices. It lives in H3 of the parameter space with Z coefficients, and you can think of that cohomology class as a higher Chern number that characterizes phases over X. So we calculated this form, or really Shweta and Marvin calculated this form in this example and integrated over S3 and found that that you get 1 when you divide by 2 pi. So this invariant is non-trivial, as expected by the non-trivial boundary anomaly. Okay, so that's nice. The other thing I want to say is, so at least for us at first, the interpretation of this form, omega-3, was a little bit mysterious, but it's possible to give it a nice physical interpretation. Okay, and it has to do with this notion of gapped quantum pumping. So we can talk about the flow, we can talk about it, we can think of it as measuring a flow of Chern number. So in order to do that, let's follow Spodeneka and Kapustin and write the Hamiltonian as a sum of local terms that are labeled by lattice sites. And this is an expression that appears in their paper. We can introduce two forms indexed by the lattice site P. And this is some maybe complicated looking expression, but if you play with it by inserting complete sets of states, what you recognize is if the site P is decoupled from the rest of the system, this is nothing but the Berry curvature 2 form for the zero-dimensional system P. That's all this is. It's just written in a perhaps unfamiliar looking way. And the details of what, there's a bunch that goes into this formula, but the details don't really matter for what I'm actually telling you. So then what can we do with this? Well, let's pick a point A in space, somewhere in space, and then we'll just sum up these two forms for all lattice sites that are to the right of A. And that's another 2 form. In an infinite system, obviously it's ill-defined. And even in a semi-infinite system, if there's some gapless point on the boundary, it's ill-defined. But in a semi-infinite system with a gap boundary, this 2 form is perfectly well-defined. And it turns out that if you compute its exterior derivative, and you can do that using formulas in their paper, you get exactly the expression for this 3 form omega 3. And in fact, the expression is a local expression near the point A that you chose. Okay, remember omega 3 depends on various choices. So here the choice comes in this choice of the point A. All right, so what does that do? Well, okay, so here's an illustration of what you can do with that in this particular example. Okay, so if you take the family over S2 cross S1 rather than over S3, so I haven't written down the Hamiltonian for that, but trust me that we can write it down. And it's convenient to look between theta equals minus 2 pi and theta equals 3 pi over 2 because the system is actually just completely trivial layer by layer in the bulk at those values of theta, and pick A to be any distance into the bulk that you want. Okay, and here I'm thinking about the kind of gapped quantum pumping version of this Chern number pump example. So here, this spin on the boundary is really just a spin feeling a Zeeman field of a fixed direction. This is some z-axis Zeeman field, doesn't depend on parameters. And here, the Hamiltonian for the spin on the boundary is our Berry phase example that we started with. Okay, so this is our this is a gapped Chern number pump. It takes you from a trivial boundary system to a boundary system with Chern number 1. Okay, and what you can do is you can say, okay, look, at the initial theta, right, this 2 form omega 2, this boundary is completely decoupled from the bulk, and so omega 2 is just measuring the total Chern number of the boundary. And at the final theta, same thing, omega 2 is just measuring the, if you integrate it, is just measuring the total Chern number of the boundary, and the difference is obviously 1. But you can also see that that difference is the same, just using Stokes' theorem, as the integral of omega 3 over the bulk parameter space, which is S2 cross S1. Okay, so this is there's some kind of bulk boundary correspondence going on here. Juven, I see you have a question.
Thanks. Sorry, I'm slightly confused by a previous slide about the way you define the induced 2 form.
Yeah.
What is the big G?
So G is just it's a Green's function. So I don't want to get into these details too much, but this is just 1 over Z minus H, where Z is just the integration variable in the complex plane. And then you choose the contour in the complex plane is just a circle around the ground state energy, which you can take to be 0. And you know, the exterior, there's a wedge product and their exterior derivatives here. The exterior derivatives are in parameter space of the Hamiltonian. That should tell you everything you need to know to unpack this formula.
Okay, so just make sure. So this complex plane is the parameter space?
Complex plane is just it's just a dummy integration variable. It's not parameter space. It's just some dummy variable that you're integrating over.
Okay.
Yeah, okay, good. So anyway, right, okay. So the point is that you can interpret the integral of omega-3 over the bulk parameter space as giving you the difference in the boundary Chern numbers. Now, this example is very carefully constructed so that, you know, the boundary is actually decoupled from the bulk at the initial and final values of theta. So that won't be true generically. But what the same consideration tells you is that actually you can think about the integral of this omega-3 more generally as measuring a difference of boundary Chern numbers, which is well defined even when the boundary Chern number itself is not well defined. If the boundary is coupled to the bulk, you know, there's no quantized Chern number of the boundary, but still there's a notion of difference of boundary Chern number, which still has to be quantized. And so that's what's going on here. Okay. All right, so now I want to tell you in the remaining time about a couple other kinds of examples. So these are going to involve symmetry now. Okay, so let's look at the classification we expect for now invertible phases of bosonic systems with a Z2 symmetry. Okay, so there's a bunch going on in this table, but we only care about really one entry. So this is just, whoops, this is just the Z2 charge in 0 dimensions. And if you go up to 1 dimension over S1, there's a version of the Phalus charge pump with Z2 symmetry. You can think of as, you know, you can think of starting with the ordinary Phalus charge pump and just breaking the U1 symmetry down to Z2. Okay, so what I'm going to do is start from this, but then I'll write down a Hamiltonian for it, but then I'll get something, and that's not really anything all that new, but we'll get something which is a little bit newer out of that system. Okay, so here's a Hamiltonian for the Z2 Phalus charge pump. Many ways to write down a Hamiltonian like this, but this is one. So this circle is parameter space indexed by theta. And at 4 points in the parameter space, I'm showing you what the Hamiltonian is for this 1D system. The symmetry is just a product of Pauli X operators. And so at theta equals 0, the Hamiltonian is just our kind of trivial Ising paramagnet minus sum on X. At theta equals pi, the Hamiltonian looks almost the same, but there's a sign difference, and the sign difference is actually extremely important in this example. And at theta equals pi over 2 and 3 pi over 2, the different sites are paired together. They're dimerized, and this is one way of doing that. I mean, there are other choices you could choose for this 2-spin Hamiltonian. Okay, and how do you get between those values of theta? Well, the sort of dumbest thing you can do works. You can just linearly interpolate, and you can check that the gap always stays open. If you do that, and if you make the system semi-infinite, you can check that it has the expected behavior for the Z2 Phalus charge pump. Okay, but that's not what I want to focus on. So, you know, we can ask a question at this point. You know, this is really a family of Ising models, and there can also be a symmetry broken phase of an Ising model. So is any similar phenomenon possible in the symmetry broken phase? Well, in the symmetry broken phase, charge is condensed, so you can't pump it anymore, but you could pump domain walls instead because domain walls are gapped. And one nice way to access that is just via the usual Kramers-Wannier duality, because that exchanges the ordered and disordered phases, and it exchanges charges and domain walls. Okay, right, you can see Xi is the operator that measures the Ising charge. Under duality, that goes to a product of Z's, which just tells you if there's a domain wall or not. Okay, so we can just apply that Kramers-Wannier duality in kind of the most obvious way to this Hamiltonian, and you get a kind of interesting system that you can think of as a Z2 domain wall pump. So at theta equals 0, you get an Ising ferromagnet. At theta equals pi, you get an Ising antiferromagnet. And what happens as you go from theta equals 0 to theta equals pi over 2, well, at theta equals pi over 2, you have an Ising ferromagnet, but only for every other spin. And the odd spins are in a paramagnetic state. And at 3 pi over 2, it's the same, but it's the even state, it's the even spins that are in the paramagnetic state, and the odd spins are in this Ising ferromagnet. And what's interesting is if you suppose you start out in the up ground state and you imagine doing an adiabatic cycle around this circle, and you ask what happens to the ground state. So what you can observe well, okay, right. So what happens is that if you start in the up state, then you go here to a ground state where the even spins are in the up ground state and the odd spins, they're in their unique paramagnetic ground state. And then that will go to this particular one of the two ground states of the antiferromagnet. And then when you go here, now it's the odd spins that are in a ferromagnetic state, but now they're pointing down. And if you come back to where you started, you actually flip ground states into one another. Okay, so that's what happens if you make an adiabatic cycle around this circle. So that's what I just said. Adiabatic cycling flips between the two ground states. And it's actually equivalent to acting with a quantum circuit, which is just the symmetry operator. And so one thing that you can point out about this sort of amusing thing to say is that you can think of this in the limit of very slow cycling, at least, as an adiabatic version of a time crystal, okay, which doesn't, no, you need to be in this limit of slow cycling, so it's different from like Floquet time crystals that we know about. But here you don't need disorder of many-body localization.
Can I ask a question?
Yeah,
So
go ahead, Dominic.
The time crystal, another feature of it is that it doesn't actually require a Z2 symmetry. Is that, do you actually need the Z2 symmetry in this case?
Good question. I think you need it. And the reason is that, so there's other stuff that I didn't have time to say about, you know, why is this, like, how do you know that this family over S1 is actually non-trivial after you've dualized? So the sort of argument you can make is, you know, you can think about this circuit and you observe that basically it takes the, you know, minimally entangled ground states to minimally entangled ground states. And so that property, right, it doesn't take a minimally entangled ground state to a cat state, and it can't do that because it's a finite depth circuit. And that will still, that still has to be true even if you deform the family away from this ideal Hamiltonian that I wrote down. And so this, you know, so this is really a robust property of this family, but that argument relies on the symmetry. And so I suspect that this can be deformed to a trivial family if you break the symmetry. I haven't shown that, but I think, but I don't see any reason that this would remain stable if you break the symmetry. Yeah, there are other, there are also versions of this same adiabatic time crystal phenomenon with topological order, and there it would not rely on a symmetry. And I'll mention that actually in a couple of slides. Okay. Okay, just an aside, I'm not going to say much about this slide because it's a preliminary result anyway, but let me just say that, you know, I've given you examples mostly of families over S1, but you can do more than that. And it's actually interesting to think about the physics of a pump, of a Phalus charge pump. And there's some interesting physics there. Let me just leave it at that. We don't completely understand it. Well, we haven't worked out all the details yet, but I think I know how the story goes there. Instead, I want to tell you just about the very last thing very quickly, which is families of non-invertible topologically ordered phases, which you can get to by gauging symmetry. So here, there are different places you can start, but let's start with bosonic systems with Z2 cross Z2 symmetry. So in one dimension, we know there's a Z2 classification of those over a point. That's just the Haldane AKLT state. So that's the Haldane AKLT chain. And so over S1 in 2 dimensions, there's a pump of the Haldane AKLT chain. So there's a nice way to think about the physics of that Haldane AKLT pump. Actually, the physics of that state is maybe even that invertible state is more interesting than you might guess naively. And the way to see that is in terms of decorated domain wall type thinking. So if you think of the symmetry as Z2A cross Z2B, just for notation, you can remember that the one-dimensional Haldane AKLT phase can be obtained by taking Z2A domain walls and binding them with Z2B charges and then condensing those composites and vice versa. Okay, so that suggests, and you can verify, that the Haldane AKLT pump constructed according to the same construction that I gave you actually is the same as taking Z2A domain walls, which are now lines in space, and decorating them with Z2B Phalus charge pumps. Okay, that makes sense because the Phalus charge pump is that's what you get when you go one dimension up, it comes from pumping the charge. So a consequence of this is what you might call flux transmutation, where a symmetry flux of the asymmetry after one cycle gets bound with the charge of the B symmetry and vice versa. So what does this mean precisely? Well, precisely it really means that the symmetry fluxes behave exactly like endpoints or spatial boundaries of Phalus charge pumps. They have all the phenomena associated with looking at the end point of a Phalus charge pump in space. Okay. So what can we do with this? Well, one thing you can do is you can gauge the symmetry, and then this flux transmutation becomes anion transmutation. So the fluxes become M particles and the charges become E particles. And so if you go around one cycle, an MA anion will get bound to an EB charge and vice versa. And there are a bunch of different phenomena associated with this. One phenomena is that some of the degenerate ground states on a torus actually get transmuted into one another. It's very similar to this adiabatic time crystal phenomenon that I talked about in the broken symmetry example. Okay. Whoops. And that's really all I have time to say about that. There are other examples in some ways, there's this even simpler example that you can get as a family of Z2 gauge theories where the E and M anions get exchanged going around a cycle. Okay, but I want to summarize since we're at the end of the time. So, what did I tell you? Well, basically, we know a lot about how to classify invertible phases over X already, at least when X is a sphere, and you can generate a lot of examples that way. Okay, and so I told you about physics of some of those examples. So one of them was this Chern number pump, and I gave some physical interpretation of this higher Berry curvature 3 form. And you can generate other examples using duality. So you can get broken symmetry examples, or you can gauge symmetry and you can get families of non-invertible phases over X. And there's a lot of phenomena that I think are interesting in these systems. And we're still in the process of exploring a bunch of these phenomena. Okay, so thanks everybody.
All right. Thank you, Mike, for the wonderful seminar. If you have a question, please raise hands.
Meng?
Yeah.
Hey, Mike. Yeah.
Hey, Meng.
It's a wonderful talk. So I just have a quick question about the last part, the gauging part. So it seems like you can basically generate example whenever you have a topological symmetry or some kind of anion permuting symmetry.
I think so. Yeah. That's my guess.
Think of it as like, I don't know, moving a domain wall through the whole system. And
yeah, I think you can. So I think we thought about this a little bit in this example, right? I mean, because in the toric code, right, you can have an interface where E turns to M and vice versa when you cross through the interface, right? So you can, so you can think of this transmutation as sweeping such a domain wall over the whole system. I think you can think about it that way.
Right. Maybe can I ask another thing about the boundary, the quantum pump that you probably mentioned or discussed in length some in the middle of the talk. So my understanding that in that case, the pump basically puts an invertible phase on the boundary, right? When we look at the boundary of this quantum pump,
right?
That means at some point, before and after the gapless point, left to and right to the gapless point, the two parts, the boundary has different faces. I mean, there's a meaning of difference between the faces of the boundary, even though the absolute meaning of phase may not be well defined. But is that an argument? I mean, does that mean that there has to be a gapless point on the boundary? I mean, I think this is what you and Dominic and Ryan were.
Yeah, that's right. Well, it has to be a gapless point. No, not necessarily. So I think, you can use that. You can probably, I think you can use that observation to argue that, okay, let's take the case, let me take a case which is a little easier for me to think about,
Right.
where X is a point and the parameter space is just S1.
Okay.
And so then we say, well, on either side of the gapless point, we have different d-dimensional phases. So whatever we do to deform the family, it's still going to be true, right? We can still look at the boundary theory for that interval in parameter space. It's still going to be true that we have a difference in d-dimensional phases from one end of the interval to another.
That's right.
And so something non-trivial will have to happen in between. It could be a gapless point. It could be, you know,
Okay.
yeah. So yeah, yeah, something non-trivial will have to happen in between. Now, I think this is subtle, and now it kind of becomes a little hard to talk about precisely. And I think it relates to some of the points that Ryan was making. If you only change parameters in the middle of the interval, I think you probably can never get rid of the gapless point, because you have to have some kind of boundary phase transition.
Yeah.
And there's going to be a gap that closes, or at least there's going to be a first order phase transition on the boundary. Now, if you change parameters everywhere on the S1 over the boundary, and then it becomes a little harder to just think about this interval. If it's a, you know, if that difference in phases is one that relies on symmetry, you can definitely, for example, explicitly break or spontaneously break the symmetry everywhere on the boundary, and then open a gap everywhere. So, yeah.
Right. But let's say it doesn't rely on symmetry, or we preserve the symmetry, then it seems hard to get rid of this gapless point.
Yeah, there may not. Yeah, there may, in that case, there may not be any way to get rid of the gapless point if you keep the boundary parameter space the same as the bulk parameter space.
But
if
how
you,
is this different from? How is this different from? I mean, SPTs can have a topologically ordered termination. I mean, this is just a kind of, this is almost like an SPT physics, right? Except it's parameterized by the this parameter space instead of like the classifying space of the group. So I guess I don't really see why it would be different from that, and why you couldn't have topologically ordered boundaries that would.
No, but Dominic, it's a bit like non-compact, right? Like you should think about these, because the homotopy type has Z's in it, you should think of it as sort of analogous to like integer quantum Hall effect, right? Which can't have a gapped boundary.
But we know that, no, if I just look at ordinary phase, I need to have a transition from one phase to a different phase, right? I cannot really get rid of that transition, no matter what I do. No, preserving all the characteristics of symmetries. And, so what, like, yeah, I'm just wondering what's really different in this boundary story.
Well, the boundary, you can't say that the boundary is initially in one SPT and it goes to a different SPT, right? If the boundary is topologically ordered, you can't really diagnose it as being an SPT.
So you mean that there is a possibility that this SPT gets trivialized by whatever is on the boundary? That's
well, that's one possibility.
That's one possibility. Yeah.
Okay. Cool. Okay. Right. Yeah, I think that's my answer my question.
Dominic.
Yeah, Dominic, did you have a question?
Yeah. So it seems like if X is some kind of sphere or something, then it's always invariants are always like pumps or pumps of pumps, something like this. But is there, if X is a more complicated space, is there an example of invariance that like cannot be understood in that way?
I don't know of such an example yet. Yeah, we're interested in finding one, but we don't have an example yet. I mean, there are sort of there are kind of there are kind of dumb examples like that, like where if X is a product of S1s, then you can have invariants that just really come from the invariant over S1 associated with different cycles, but that's not really anything new. So the question is, you know, whether there can be something, yeah, something that doesn't qualify. Something that really that really comes from, that's really something new associated with spaces that are not spheres. But I don't have an example like that yet.
Right, thanks.
Well, couldn't you just take the total space to be something like not a sphere, right? Think about a family on RP3 or something. I don't know of an example that occurs naturally.
Right. I mean, that's right. That's what you would want to do. Sure. Yeah. One of my collaborators is telling me that there should be plenty of examples. So we should go find some. But we don't have them yet.
I also have a question. Dominic, do you have more?
Oh, no, sorry, I'm done.
My question is that if you consider the Hamiltonian, the class, and the parameter space, is it possible to include like subsystem symmetries? And if you further gauge, can you also include like non-invertible places with fracton order? I'm not sure whether these are the rules.
Can you say the first part of the question again?
Can you include?
I'm just not quite sure I got it.
Can you include subsystem symmetry in the Hamiltonian?
Yeah, I haven't thought about that, but I mean, certainly, yeah, as a general matter, sure, you can certainly do that. And I have not tried to think about such families yet. And I also think that there are probably interesting fractonic families, but I haven't tried to think about those yet either.
Thank you. Probably not classified by groups for the fracton, right?
Yeah, I mean, I don't think we really know how to classify even phases over a point for fractons. I mean, not that we know nothing about it, but we don't have the sort of very well developed theory that this starts from. So it's kind of, I can think of ways to generate examples there, but it's not going to be, here we kind of have this big machine that we can use to generate lots of examples. So I don't know what that would look like in the fracton world. Probably we don't know the analog of that, at least not yet.
Mm-hmm. Okay, thank you.
Fiona, you have a question?
Yeah. So you gave a bunch of examples of things that you can do, sort of cycles that you can carry out adiabatically that have these interesting responses. But I guess do you have is there some simple way of thinking about what kinds of cycles are not possible without sort of closing this gap at some point?
Yeah, so I guess, I mean, maybe I could interpret that as a question about anomalies, right? So that's, I mean, in some sense, that's the topic of this work that I mentioned by, well, let me just show the authors in case I forget somebody. Right, so this work by Cordova et al. That's one of the topics of that paper. So yeah, I mean, so from the point of view of what I'm talking about, if you think about the boundary theories for any of these interesting families, right, there will be some kind of obstructions to trivializing the boundary over the parameter space, right? So you can have theories that are, like the sort of typical thing. I mean, okay, so a good canonical example to think about, because it's so simple, is the end state of this Chern number pump, because that's just a zero-dimensional boundary theory. Well, there's a single while point over S3, so that's clearly anomalous. There's clearly an obstruction to gapping out that zero-dimensional system over S3. Well, and it tells you that it's not an ordinary zero-dimensional quantum mechanical system over S3, even though every individual system, if you just look at points in that parameter space, there's nothing anomalous about individual systems, or even if you just look over neighborhoods of S3, there's no anomaly. You only see it globally if you look over the whole parameter space.
Right, but I guess, like, I was thinking of that as some statement that you can construct, a Chern number pump, right? But maybe I think there's another question, which is, suppose I have two different, phases, A and B, right? And I want to ask the question, is it possible to construct a cycle that gets me from A to B?
Oh, well, if A and B are invertible phases, I think it's always possible. If they're invertible phases with the same symmetry characteristics and whatever over the same parameter space, then yes, I think the same construction I showed will give you that cycle.
Okay. And you can so the point is there's no situation in which you can't do that without closing the spectral gap somewhere.
I think so. Although I guess, I have to think about like, what does it mean? Yeah, what does it mean to pump between A and B? Okay, let me make the same statement just a little bit less confidently. I think I know how to write down a model that you can interpret in that way. And yeah, I see. Oh, yeah. Okay, no, now I'll become confident again. All right, I was thinking about this in real time. Yeah, so the way you do that, right, the thing that will pump between A and B on the boundary, you just look at the invertible phase, which is the difference of A and B, right? So A stacked with B inverse. And you just and then you run exactly the same construction I showed you, where the thing you're pumping in the boundary is A stacked with B inverse, and that will do it.
Okay.
So more generally, yeah, there might be questions like that if A and B are not invertible phases that are harder to answer. But then it gets a little tricky, like what does it mean to pump between those two phases on the boundary anyway? I'm not sure that maybe we don't understand yet, if it makes sense even to think about that kind of question.
Okay, thanks.
Okay, any further questions for Mike? Last chance. Okay, if not, let's thank Mike, Professor Hermele again. Thank you very much for the wonderful lecture. Thank you.
Thanks, everyone.
Thanks.
Do you have, Mike, do you have some time to chat for a minute or two? No.